Alright, so in this video we're going to discuss the equilibrium condition for 3D force systems on a particle. So if we have, when the acceleration on a particle is equal to 0, the particle is in equilibrium. We know that from Newton's first law. And then we know that Newton's second law states that the force on any body is proportional to its mass times its acceleration. So if its acceleration is 0, the resultant force or the net force on the particle must also be equal to 0. So for um, for 3D, what that is saying is that the sum of all the forces on a particle is going to be equal to 0, and we can say that's the same thing as the sum of all the forces in the x direction times the unit vector I plus the sum of all the forces in the y direction times the unit vector j plus the sum of all the z forces in the z along the z-axis times the unit vector k. So since we know this has to be equal to 0, the only way this can be true is that the sum of the forces in the x has to be equal to 0, and the sum of the forces in the y direction has to be equal to 0, and the sum of all of our z components of our forces also has to be equal to 0 for equilibrium to exist. Okay, so using these equations, we can so using these three equations, we may solve for any three unknown forces. So I should say three unknown force magnitudes. Alright? Or we can also solve for the direction of the vectors, so alpha, beta, and gamma. Okay? For any force. Alright? So but we can only solve up to a maximum of 3 of those. All right, so when we are trying to analyze the equilibrium on a particle, the first step is we're going to draw our free body diagram. There's 3 key aspects of drawing our free body diagram. The first is that you need to define the orientation of your particle. So in order to do that, you're going to define your x, y, and z axes. The second step is you're going to then, once you have all your axes defined, you're going to label all the forces that are acting on your particle. So you're going to label all known and unknown forces and the directions. All right, and the last thing you're going to do is you're going to assume the sense or the direction of a force with an unknown magnitude. Of any forces, I should say. Any forces with an unknown magnitude. Okay. So after your free body diagram is complete, you're going to then apply your equations of equilibrium. So for the equations of equilibrium, you can use either of the following two methods. The first method is the scalar method. So what you would do is you would separate all your forces into their x, y, and z components. And then you would insert these components, the x, y, and z components, into their respective equations. So you would put all the x components into this equation. You would put all the y components of all the forces acting on the particle into this equation. And you would put all the z components acting on a particle into the third equation. So the second way you can do this, and you're doing the same process, you're just representing it a different way, is that you can use vectors to do it. So what you can do is that you can write each force as a Cartesian vector. Then you can calculate the resultant force using those all the forces as a Cartesian vector, and then you can set all the components of your resultant vector equal to 0, and then you can solve that. So what that ends up looking like is you can say the resultant force is equal to the sum of all your forces in your system that are acting on the particle, which would be equal to 0I plus 0J plus 0K. All right. All right. So in any of these, so for either of these two methods, the one thing I'd like to we should remind ourselves is that after we solve for the unknown magnitudes of our forces, we may end up getting a negative answer. So we might end up solving for an unknown force's magnitude, and it might be a negative number. All right. If we get a negative answer, what this means is that the direction of the force is actually acting. Direction of the force is acting in the opposite direction as it's drawn on our free body diagram. All right. So just to recap, for 3D Cartesian vectors, we defined our equilibrium condition as being the sum of all the force, as our resultant force has to be equal to 0. So that ends up giving us three scalar equations. Sum of the forces in x is equal to 0, sum of the forces in y is equal to 0, and sum of the forces in z direction is 0. And to analyze the equilibrium of a particle in 3 dimensions, we're going to follow the procedure where you first will draw your free body diagram. You'll define your axes, you'll label all the forces, and you'll assume any directions of the forces, and then you apply either the three scalar equations of equilibrium, or you apply you'll sum all the forces together as vectors, and then set the components equal to 0 afterwards. All right.